Hello everybody. Today I want to talk about the thermodynamics of compressible flow. Compressible flow. And in this video I want to talk about the speed of sound specifically and how we want to derive an equation relating thermodynamic properties to the speed of sound. Speed of sound, which we will just call C in this case. It's not the speed of light, it's the speed of sound. And you know from experience that speed of sound will be different in differing conditions. For example, it's a lot faster in water than it is in air. And in a moment you will see why that may be the case. So first of all, we want to kind of conceptualize what a sound wave is like in the air. So for example, let's say you have a speaker and you have me with my bass guitar. I'm sorry I don't really make bass videos that much these days, I'm quite busy. You have my bass guitar, and this guy is connected to an amplifier and a speaker system. And if you look at the speaker, you actually have some kind of a cone which vibrates up and down to give you the bass, dooms. Every time you hear that dooms, or that sound you hear, this thing will be vibrating about 20 to 40 times a second, about 20-40 hertz. That will give you the bass sound. But what is it actually doing to the air around it? Let's say you have a very simplified speaker system. You have some coils here. I don't know how that works exactly, and we're not going to be too concerned about that. But every time the speaker produces sound, there is a force. There is a force that is being exerted on surrounding air. So when this happens, the speaker actually moves forward a bit, and it forces the air very near to it to actually go that little bit faster. Let's call it dvx. A little change in velocity will be called dvx. But you see, the air right in front of this wavefront is actually still. Let's take an axis here and we'll label to the right as positive for easier reference. So where then would you actually quantify the speed of sound? Let's say we have that little change in velocity again, and this is the boundary where, let's say, the air to the right of this boundary is actually still, and the air to the left of this boundary is actually moving at dvx. Alright? So let's say this is a snapshot at t equals to t1, and I take another snapshot, let's say a few seconds later. I'll draw some arrows, and all the particles here have a speed or velocity of dvx. And to the right of this boundary, as usual, the air will be still. This will be at t equals to t2. Now what happens? From the boundary being at t equals 1 to the boundary being at t equals 2, you see that the wavefront has actually moved just a little bit. A little small distance, delta s, or ds, however you like to call it. If you are using differential analysis, then you might want to use ds, but for simplicity, we'll just use delta s. And you see the time between these wavefronts, delta t equals to t2 minus t1, and the speed of sound will actually be c equals to delta s over delta t. Alright, so this is just, you want to clear up any conceptual errors on what the speed of sound is. It is not this dvx, it is not that dvx, it is the speed at which this wavefront actually moves from left to right. So you might be wondering, hey, shouldn't the sound wave be oscillating? And yes, you are right. In fact, if you have the speaker here and it starts moving back, it will impart a force on the air surrounding it this way. And then you will have another wave here, where to the left it's moving at the speed of this speaker, and to the right it's moving here. So that will be actually how the complete sound wave would be like, going back and forth. I'm sorry it's a little messy, but I hope you get the concept there. But for now, we just want to look at the boundary here, because all you need to determine the speed of sound is to consider how fast this boundary moves from here to here. Excuse me. Now, how do we want to do that? Let's consider this control volume again. These guys will be moving at dvx, and this is the still air. And let's say to simplify things for ourselves, let's say this thing is moving to the right at the speed of sound. So if that is the case, you actually have to change this to 0. And you want to redraw this diagram, this control volume. Yeah, you want to make it moving at the speed of sound, but this is not actually the speed of sound. I mean, this reference frame, control volume 1, is not moving in the speed of sound, but we want to simplify it here. So this is v equals to 0. And we want to move this here so that the control volume is actually moving at the speed of sound. Next, how are we going to do this? Let's say the air here, this is v equals to c. Let's say the air here is coming in at the speed of sound now. Alright? And let's say the air is leaving the system of this wavefront at c minus dvx. Is it c minus dvx? Oh, if it's moving at c and outside should be moving at c plus dvx. Alright. What is c minus dvx? Okay, let's clarify this. Let's say this is still air. This guy is moving at 0. This wave front is moving at c. So to transform this, these guys will have to move back at c. These guys will have to move back at c. So it's c minus dvx. All right, no confusion there. Okay. Let's draw a new control volume 2. This is the inflow, and this is the outflow, which will be moving slightly slower. Alright. And since we are talking about compressible flow, we'll definitely want to look at the density changes of between the left and right of this boundary. Okay, just to tell us this control volume is moving at c to the right. Alright. And since sound is a pressure wave, we want to be looking at P as well. So these are the two main thermodynamic properties we'll probably be wanting to look at. Now, as usual, once we have our control volume, we can start having a mass and energy balance. But in other cases, you might want to use momentum balance as well. But theoretically speaking, you can use any one of these two, as long as you have the mass balance inside. Meaning to say, you can use a mass and energy balance, or you can use a mass and momentum balance. But in an engineering field, we want to use whatever is most convenient and most accurate. So what we might want to do is to use the mass balance and the momentum balance. Because if you use energy balance, there are a lot of confusing terms, a lot of friction. You may not know the change in internal energy, etc., etc. But when we talk about momentum balance, you can just talk about the forces acting on the system, which is quite obvious to see using this control volume 2 as your diagram. Alright, let's first do the mass balance on this system. We have inflows at C, and we have outflows at C. Sorry about that. Minus dvx. Alright, so the basic mass balance equation, dm dt, equals to summation of all the mass in minus summation of all the mass out. Alright, this is a mass balance, conservation of mass. So let us first assume, for simplicity's sake, that it's a steady state. Now, from your conceptualization of sound waves, you think that okay, sound's very unsteady, it's all over the place, it's very messy. But when you look at the individual waveform itself, you can see they are very nicely smooth. They're quite smooth, and as long as there are no other sound waves around, they should remain pretty much the same. And if there are other sound waves around, you'll probably use a principle of superposition. But we won't be talking about that right now. We're talking about a solitary sound wave. If it's a solitary sound wave, then hey, there shouldn't be that much change with respect to time. But, when we talk about the mass coming in and out, if the C is constant, then here is constant, and this is constant as well. Right? So we assume steady state. That means anything with respect to time equals to 0. I shall just cancel this off. Alright. The next thing will be a very obvious conclusion. The sum of all the mass in will be the sum of all the mass out. It's easy, right? Let's say we just have one stream in and one stream out. Okay? So this is m dot. This is the rate of mass flow in equals the rate of mass flow out. So since this is compressible, we need to look at the density and the volume in, the volumetric flow rate in, and density and the volumetric flow rate out. So rho in, V in equals to rho out, V dot out. Alright? Okay. What's next? We want to know what is this V in. We just look back at our diagram. You see that, okay, we have air coming in at the velocity c. So V in equals to C in, or rather just C, and A. Alright, that's the volume in, and let's look at the volume out. Okay, A is actually just, let's say we have an area here, and this is like a 3D block of some sort. We have an area here. So the volumetric flow rate is the C, speed of sound, times this area here. Let's say it's a cuboid area or something. Alright, whatever. So this will be the area. Now we want to look at the flow rate out. That is C minus dV. That is the speed out. This will be C minus dVx. Now let's substitute this back into here. Rho in, V in equals to rho out, V out. Rho in CA equals to rho out, C minus D Vx of A times A, not of A, sorry. So for simplicity's sake, let's just cancel the A out, because we don't need to really bother about that. Rho in C equals to rho out, C minus dVx. Alright, so next thing, what is rho in and rho out? Alright, we have a rho in and rho out. So rho in, what's the stuff coming into the system? It's just rho of the surrounding fluid or surrounding air or surrounding whatever, you know. So this is rho surrounding, which I just call rho for simplicity's sake. Rho out, you see that the sound is actually a pressure wave. So when I actually compress this S slightly, the pressure will change and the density will change. So to generalize this change, I will just have rho plus d rho. and whatever you want to look at the pressure too, right? So whatever pressure that's coming in, it will be a pressure of the surrounding air or the surrounding fluid. We just call that P, and the P out will be equals to P plus dP. Clear about this? P in is the pressure of the ambient surroundings. P out, since there's a sound wave, there's a small little change in pressure. Alright, so this pressure will change just a little bit. I'm going to substitute that back into our equation. So we have PC and P plus dP, C minus dVx. C minus dVx. Both sides are equivalent. Let's multiply out the terms. So we have PC minus P dVx. This is velocity, not volume. Next we'll have plus C dP and minus dP dVx. First thing first, let's simplify this. Cancel these PC terms. Let's put down this P dVx term plus C dP. Oh, I'm so sorry. This should be rho. This shouldn't be P. Yes, it should be rho. All these terms should be rho. Now let's just write it a little nicer. Rho C equals to rho plus d rho. C minus dV of x. So rho C equals to rho C minus rho dV of x plus C d rho minus d rho dV of x. Let's simplify this. Rho dVx C d rho minus d rho dVx. Now what is this term? This is a very small change. This is also very small. So all in all, this is very, very small. We can neglect this because when we compare this term to this term and this term, this is really small. So we just ignore it. So in the end, we'll just have rho dVx equals to C d rho. And let's just make dVx the subject. dVx will be C over rho d rho. This is our mass balance. Some people call it the continuity equation. I just like to call it mass balance. Alright. Stay tuned for part 2. I will explain more on the speed of sound because we have one thermodynamic property here, but we don't know what this is. This is not thermodynamic property. Alright. Thanks for watching. Please watch the next video. We'd like to invite you to watch the next video. Thanks. Please subscribe, rate and comment. If you have any questions, please post it in the comments section below. Thank you very much.